Large cities can be a complex network of interconnected and layered streets, and planning the most efficient route between point A to point B can be a challenge, especially in an unfamiliar area. Not too long ago, multi-page street atlases were a traveller's best friend. The amount of planning required to get to a destination depended on the complexity of the city to be navigated, and a route could span multiple and non-consecutive pages. Today, street atlases are relics, replaced by map applications in which an origin and destination are entered, and the recommended route is automatically displayed. Virtually no planning is required, and the odds of ending up at the wrong location are quite low. Much like navigating a big city, an electrical signal in a test system can be routed through a complex network of interconnected relays, wiring, and interfaces. In large switching systems, a route could span multiple and non-consecutive schematic pages. Instead of directional terms and street names, software engineers must determine the module identifiers, relay names, and switch settings required to establish a path between a test instrument and a DUT test point. This can be a time-consuming exercise, with any code errors leading to delays in deploying a system into production. A simple example helps provide context to the challenge. A multi-port device is routed through a switching system to a power meter and spectrum analyzer. The switch is designed as a matrix, using PXR relay modules interconnected with coaxial wires. To make a peak power measurement of channel 16, we need to ensure that all switches are correctly set to establish the correct route between point A, channel 16, and point B, the power meter. A traditional software approach requires deep understanding of the schematic, noting the module IDs and switch settings that establish the path. Every switch closure requires a line of code. For example, the first line of code connects position 4 on relay K2 of PXR module 2 to its common, and the references in the code to the switch positions COM2 and channel 4 are generally meaningless to someone unfamiliar with the schematic. While this is a trivial example, it still requires 4 function calls to establish one path for one test. If there is a simple typo in the code, the correct path would not have been established, resulting in wasted time debugging test failures. Ideally, a programming methodology would exist that provides a switch programming experience that is analogous to using a mobile map application. Introducing Switch Path Manager, an interactive utility that maps a switch system schematic into a software configuration file that simplifies code development. This mapping is a one-time effort in which all external connections between relays and modules, as well as intuitive endpoint names, are defined. This configuration file, defining how endpoints are connected to one another through the switch network, can then be referenced in application code through the SPM application programming interface. In the example, one line of code using intuitive endpoint names can be called through the SPM API to correctly set the position of all 4 relays in the path. The result is code that becomes much easier to read and maintain. Sometimes trip planning requires flexibility in route options. For example, avoiding highways or roads with a toll. Building flexibility in switching software can also produce significant benefits. A cross-point matrix allows any input to be connected to any output without restrictions, such as in an 8x16 matrix, where, for example, closing 2 relays, input Y3 is connected to output X4 and input Y5 to output X6. This introduces flexibility into the system design, but also presents opportunity for damage if 2 incompatible endpoints are inadvertently connected together. Let's connect a power source and system ground to a device under test through the matrix. Power and ground are connected along the wire rows, and the DUT power and I/O channels are connected across the X columns. To verify how the DUT behaves when its input power is shorted to system ground, the relay at X1 Y8 cross point is closed. If the power source is then connected to the DUT by closing relays at X1 Y1 and X2 Y2 cross points without adding a line of code to disconnect the X1 Y8 relay, the source is shorted to system ground, likely welding the relays. To prevent going the wrong way down a one-way street, SPM gives software engineers the ability to define protection behaviour. By defining an endpoint as part of a protection group, incompatible connections are prevented. Power and ground protection groups can be defined with appropriate endpoints included in each group. The Attempts to make connections between two incompatible points are rejected, and a runtime error prevents the connection from taking place, protecting the system from a catastrophic failure. Thank you for watching this introduction to Switch Path Manager, an innovative software utility that is helping manufacturing organisations accelerate the deployment of test systems into production. For more information, please visit our website at pickeringtest.com/SPM.